Okay. Thank you very much to the organizers. Such an honor to be introduced by Diego. Okay, good. I must say, I agree with what Diego just said. If there's anything worse than axion dark matter, actually, axion dark matter is very good in my opinion. Dark photon, dark matter, this talk will be mostly about complaints, probably. So, but there are a bunch of experts in the room, so keep me, interrupt me. Good. So, why am I talking about this? I mean, I would rather talk about other topics actually that I've been interested in the past few years. But I think for this workshop, the one that would come closer to this kind of audience is this topic. So my take is we don't know yet what the dark matter is. So there are a bunch of theoretical models, as Kim already told us, spanning so many orders of magnitude in masses. And these days, there is a lot of research going into very light dark matter. And to have very light dark matter, you need to have bosons, not fermions. If you have fermions, you cannot go below 100 electron volts because of the Pauli exclusion principle. With boson, you can go as low as you want, pretty much, right? So axion is an example. Another example, instead of spin 0 like the axion, could be spin 1, vector dark matter. Still a boson, so you can pack as many bosons as you can, as you want, I would say, and have a very light dark matter candidate, which could be interesting, I think, for this workshop, in the sense that maybe can have some behavior at some scales, hopefully even at scales relevant for LSS, that are peculiar, okay, to this type of dark matter rather than the usual WIMP, say, okay? So that would be why now we would be interested, I would say, in studying this thing. So to think about low mass, long wavelength dark matter. Very good. Now, a very quick recap. This was already in a slide by Kim. Okay, if you have a scalar, let me write the action also. Oh, if I write too small, please tell me. Okay, let's just have a free scalar with a mass. If you look at the homogeneous mode, which just means, let me write everything for now. And right, so this equation already appeared in Kim's slide. If I want to look at the homogeneous mode, which is the mode that doesn't depend on space, but only on time, okay? So there are no gradients. Forget about that term. So you already saw this equation, and you know that this equation describes right, you have some initial conditions, say the field starts at some phi 0, and then you have the quadratic potential. As long as Hubble is larger than the mass, the field is stuck, is frozen, right? Dark energy. When Hubble evolves and becomes smaller, this oscillator now is underdamped, and the field can oscillate. When it oscillates, it behaves like matter. Now, one thing that I would say is that as long as it's stuck, this is relevant for later, its energy density is constant. By that, I mean it doesn't redshift. That's why it behaves like dark energy, okay? This is an important point. It's trivial for the scalar, but we'll soon see what happens with the vector. And another comment that I wanted to make, because people, this is probably not the case for this audience, but let me make the comment anyway. So people sometimes are confused that, so with this game, the mass can be as low as you want. Whatever the mass is, you get cold dark matter. Actually, this is the coldest dark matter you can get, and the reason is, if you look at the homogeneous mode, what you are exciting in these oscillations, so these oscillations are classical. If you describe these by quantum mechanics, what you're really exciting are only zero momentum modes, okay? So you pack a bunch of bosons with zero momentum, exactly zero, that you populate that. So this thing, whatever the mass is, can be as small as you want. The momentum is zero. So this is cold, by definition, the coldest, okay? Good. So, vector. Let's go down here. So now the action let's see how many terms. Yeah, let me write this for now. And let me be pedantic also with this. Okay, so now F mu nu is the field strength for the dark photon, okay? F mu nu standard model is the visible photon. So I also wrote the kinetic mixing, which is allowed to write. And chi, I call chi is dimensionless, is the kinetic mixing. So there already is a very large experimental effort trying to detect dark photons, okay? And pretty much all the detection strategies exploit this kinetic mixing. So typically, when people search for dark photon, dark matter, a typical plot is in this kinetic mixing versus mass plane. And plots, okay, I'm gonna attempt to do a plot. It's gonna look bad, but okay, we'll see. So let's say 1 for the kinetic mixing. Down here, I put something very small, 10 to the minus 18. Remember, this is dimensionless. Let me put a 10 to the minus 5 here. And the mass range for a somewhat typical plot, this mass I measure in, electron volts, okay? And up to something like 10 to the 5. Can be even larger than this, by the way. But just to give you an idea, because what I want to get at is the following. Let me put a 10 to the minus 15 line here for the kinetic mixing. And something like 10 to the minus 3 here. So there are some constraints, okay, that look something, it's gonna be very sketchy, something that goes down like this, and something. And there are more constraints all over this plot. But just to show you these constraints, so the reason why I'm drawing just this line, so the region above here is excluded by a bunch of running experiments and foreseen experiments that people are thinking about. And the reason why I'm only showing this line, which is very sketchy, you can go and check many papers online to see a much better version of this plot, is to say that this line assumes that the dark photon is dark matter, okay? So now the question is, how can I think of mechanisms in the early universe to produce dark photon, dark matter in these regimes? And I'm gonna already give you like a very brief answer right now. It's very hard, actually. Very, very hard. So let me guide you through why it's actually very hard. So first thing you can think of doing, let me, so there was a first proposal by Jacob Scholz and Ann Nelson. I hope I spelled Jacob's last name correctly. So this was 2011. Oh, another side comment. So the misalignment for scalar has been known for decades, okay? So people realized there could be a mechanism like that already in the 80s at least, maybe even in the 70s, okay? And it's robust, it works, it's fine. It took a much longer time to come up with ideas for the vector. So the first paper I'm aware of is this paper in 2011, where they said, okay, for a second, forget about the kinetic mixing. So now I have kinetic and mass term. If you write the equation of motion for the gauge field, you get something like this. Okay? Again, I'm looking at the homogeneous mode. So now you look, this is not a mistake, there's no 3 in this equation, it's really this equation. So you compare this equation to the one above, it's very similar, okay? So you would say, can play the same game. I gave AI 0 some initial condition, okay, even if it's a vector. It's frozen there until h is larger than ma squared, and then it oscillates, okay? Doesn't work. The reason why it doesn't work is because Remember, if I fix the scalar phi 0, the energy density is constant. But here, I mean, the point is exactly in the way this mass term is, no? So if I look at that, right, I know that the, let's say, sorry, let me write it like this. The energy density in some initial configuration, which is displaced, say from the minimum, is given by so the g mu nu, which is there for the spatial components, contains a 1 over a squared, the scale factor. So if I try to put the vector there, the energy density is not constant. It's going to redshift away. So this guy is going to lose its energy density. I have no more energy density available, so no oscillations to talk about. That's one way of looking at it. Another way, which I'm going to write because it's useful for the next things I want to discuss, is you can think of this field written like this as, again, this is a vector, so it's like the momentum. There is the comoving momentum and the physical momentum. So I can think of this AI as the comoving field. And I can define an AI bar, which is, by the way, it's important that the index is a low index here, okay? So, and this is, I would call this the physical, okay? If this is confusing, ask me. I can tell you a couple more words about this, but let's push, no? So in terms of this field, the equation of motion looks like, let me write it correctly. So now from this equation of motion, it's already explicit why the vector doesn't work. So when you go to the physical field, say, okay, you see that the driving force of the oscillator is not simply mn squared. By the way, now the 3 reappeared. So now this equation is really one-to-one correspondence with the scalar. But now you see there is inevitably an h squared contribution to the mass term for the physical field, which means that even if you set m to be very small, the oscillator is driven by h. So if you compare this to the damping force, this guy is not stuck. It's moving, it's rolling down, okay? So that's another way of thinking about this. And let me point out that this combination, oops, is 6 times the Ricci scalar, okay, in a curved background. And the reason why I'm pointing this out is because a year after this proposal, which doesn't work, there was a big paper by Arias and company where they say, we know how to fix this. No? This equation suggests also the fix. Let's add to the Lagrangian the following term, which is right? So if I add this term, what happens is that this comes here, right? Oh, sorry, I should also, given my signs, and by the way, maybe this is mostly an audience of cosmologists, so maybe everybody's fine, but for particle physicists, we typically use the mostly minus metric. Here I'm using the mostly plus, so that's why, for instance, for the scalar, I have both negative signs for kinetic and mass, okay? Just so here, instead, I need to put this term with a plus sign, okay? And the way this enters here now is with the minus psi r. Good. So now you see that just by fixing this psi is a dimensionless coupling again. I fix it to 1/6, which is also the famous 1/6 for the scalar to make the scalar conformal, okay? So if I fix it to 1/6, this term cancels exactly this one, okay? So it looks like I can declare victory, right? So now I am back to the exact equation of motion as for the scalar. So we would say, oh, good, it works. That's what they claimed in this paper, okay? Doesn't work either. The reason why it doesn't work is because by adding this, and yes. Oh, sorry, no, you're right. This is R/6, not 6R. Thank you. You see, I wanted to see if you were paying attention. Thank you. Very good. Yes. So the sign, again, is important. Here is a minus sign. When you do this shift, now I'm not going to write it down because I'm too slow, but you can show that if you look at the longitudinal mode, now remember, I have a massive photon, so the massive photon has 3 polarizations. If you look at what happens to the equation of motion for the longitudinal modes, you see that there are several k modes of the longitudinal mode that become tachyonic, okay? So this system, this model, has a Gaussian stability. Kind of ironically, this was known in the literature. There were already papers, so this paper was written in 2012. There were papers by Cataldi, Peloso, and company in 2008 and 2009. They were interested in other things, not in dark photon, dark matter, but they had already very clearly pointed out that if you play this game, you develop Gaussian instability, so your model doesn't make sense. Okay, yes? Yes. During inflation is certainly a problem, exactly. Yes, later on, right, but later on, put it this way, right? I mean, for the scalar, why does a scalar work? Why do we expect a phi 0? We expect phi 0 as a result of inflation, right? Inflation displaces the field. So here, if you say, I'm going to play this game in radiation domination era, then you have to tell me how do you displace the vector to begin with, no? So typically, we think of these things during inflation to have a reason to say why the field, not because of quantum fluctuations, get an effective classical expectation value, I would say, right? So, yes. Ah, very good. So I was about to quote, so let me also write this. So there were more recently, let me write it here. So I should include this because, so, oops, this is an A. So Capanelli, Jenks, Kolb, and Mac. So for your question, I would refer you to, there are 2 papers actually. There is a short paper, which I think is a PRL, whatever, and the longer paper. So what they do is they not only, they consider this coupling, they also consider, if you call this one, there is schematically also this coupling with the Ricci tensor that you can write, okay, and that's it. So they go very systematically. They go through this. They ask, they require that there is no Gaussian stability, okay? So you can, you have a couple of equations and you have enough room for impose this condition. So to impose that there is no Gaussian stability. Even after that, when you check the dynamics of the system, they still find some runaway behavior. So there is still some tachyonic instability anyway. And if I remember correctly, I should relook at this paper because actually the long paper I never read carefully, I read the short ones. But they also try to find fixes, not to this runaway behavior, adding other ingredients. And they try at least 3 different fixes and none of them work. And they say this explicitly. So apparently, even if you fix the Gaussian stability as they do, they're still, I mean, it seems, this thing seems to be pathological. It's very hard to cure. So this is very recent, more recent work done on this, along these lines. Okay, so people didn't give up, okay? Theorists typically are creative, so they keep pushing. They say, but I want this misalignment to work, so let's try something else. So there are a series of papers. Nakayama is in almost all of them, so I'm not going to do justice to the other authors. But if you look for Nakayama, you can find all these papers. So maybe they have one even before this, but the ones I'm aware of are at least until 2023 and counting. So there are several. So What's maybe another way around this? So forget about this Ricci, the coupling to the Ricci scalar. Instead, modify the kinetic term. Oops. Oh, tell me if you cannot read my writing. Walter, yell at me if you can't. So what you want to do, well, I mean, what you can do is go from, so you multiply the kinetic term by a function square, just for convention, the square, whatever, of a scalar field. Typically, the scalar field will be the inflaton, okay? So what happens if you do that? For now, I don't even have to specify what the scalar field is. I'm just telling you I'm modifying the kinetic term like that with this function. And now I rewrite that equation of motion up there. Actually, first, oops, because I modified the kinetic field to have the, let's say, physical field canonically normalized, I have to slightly change my definition. So this again was ecomoving, this is the physical, it includes F, not F squared, just F, okay? So this will have the canonical kinetic term and it's the physical field, if I define it like this. Now, if you write the equation of motion for this field, what you find is this. Now I have to remind myself. So it looks like, this was as it was before, and then you have okay, good. So it does something, okay, as you see. And now take, for instance, I didn't leave much room for me. Okay, take this F squared to be proportional to the scale factor to some power of alpha, okay? I will get to some one actually explicit model about that. But for now, just take that. If you do that, this becomes minus alpha plus 4 plus 2 minus alpha over 2 h dot. Okay, just plug it in, that's what happens. Now you see that if I construct a model where I put a function of the scalar field that is proportional to this power of the scale factor, and if I manage to construct it such that this power is either 2 or minus 4, during inflation, for instance, this would work, right? I get rid of this term. In inflation, this I don't have, okay? If I'm out of inflation to get rid of both, I only alpha equals 2 works, okay? But then I'm back to having no, something that could work. No? I fix my initial condition, it's stuck there until Hubble goes below the mass. So it seems that this could work. Good. Now, let me go back here. Now, now this is the question. So the question is really, what is the F? So, so take phi to be the inflaton, okay? No, now you're laughing, but now then I think you will, hopefully, well, we'll see. So if phi is the inflaton, I mean, let's suppose phi is the inflaton, and let's take, as an example, a monomial potential, okay? So the phi to some power n. This is the inflaton potential. Then, what you need to play that game, you need f squared of phi to be, I have some, c is just a number, And you can check that in a model of inflation like that, if you ask this f function to have this form then corresponds to this AN is the value of the scale factor at the end of inflation, okay, to this power C, where C is the whatever coefficient that I put there, and N is the power of the monomial. So if you look at that board, that means that in this model, this alpha would be minus 2Cn. So what do I want to get with this, and why I wrote what the F, right? Because so to play this game, you need this behavior. To get this behavior, you need to build up a model to give you something like this. But this is highly non-trivial. I mean, model building, if you want to achieve something like this, I don't even know what you have to do. I mean, people would put this there ad hoc, no? But I don't know, it seems kind of far-fetched. Okay, it's, in my mind, it's kind of epicycles, okay, when you go to this. Okay, so bottom line for this kind of section, if you're really persistent, not like these people are, you can force it and do it. Well, actually, wait, I have also to put a parenthesis here again, because I mean, it looks like you can do it. Then when you look at the outcomes, okay, of these models, you run into very severe constraints from isocurvature perturbations. You have constraints from anisotropies, even in the adiabatic curvature perturbations. So it turns out that if you couple something like this to the field, this is excluded, okay, by these observations. And then it means that, okay, you couple some phi with this behavior, but this phi cannot be in the inflaton, because otherwise you run into those constraints. So then you add the curvaton to the model. And still they have some trouble, and that's why they have a series of papers, because at every step they find a new constraint, and so again, it's somewhat pathological, okay? You can keep pushing and find ways around every obstacle, but it's compared to the scalar, to me, this is kind of screaming, like I don't want to work. In this recipe, the longitudinal mode is fine, yes, exactly. Yes. 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 Again, indeed, there are ways around all these obstacles, but you have to keep, yes, moving some things around. I mean, you also had the... Maybe you're going to talk about this already, right? But all of this problem is because you're insisting that yes. I'm just going to switch indeed to forget misalignment. Very good, yes, okay, good. So this was a long story to tell you that, okay, people worked hard not to say misalignment must work also for the vector. It seems it doesn't really want to work to me, okay? I'm not going very sequentially with the blackboard, but okay. Good, so indeed some people gave up much sooner than all these papers, okay, on this misalignment and tried something else. So what's the something else? By the way, it's very warm in this room. Just, okay. So, okay, back in time. I think this is exactly what you wanted to hear. Good, so 2015, these three gentlemen wrote this paper that is amazing in my mind still today, okay. And here, okay, let me just rewrite quickly. We go back to the basics, really. So I'm going to be shorter, but I mean, it's the same action as above. Now, so kinetic and kinetic term and mass term, period, only this. Now, what did they point out? They point out that the longitudinal mode, and maybe I should have written for you, but I didn't. Right, okay, I will just explain in words. So So you can think of the longitudinal mode if you go, I actually will get also to that point, maybe, if time allows. So this is really an effective action in some sense, because you would call this the Proca action, okay, where I just wrote a mass term brutally, okay. If you think of a Higgs mechanism, then the longitudinal mode is the Goldstone, which is a scalar, right, that gets eaten by the vector, right? So really, the longitudinal mode of the vector behaves like a scalar. And as everybody in this room knows very well, a scalar during inflation acquires quantum fluctuations, right? So does the longitudinal mode of the vector. So these quantum fluctuations, so just let me write, so this is really equivalent to a scalar. And because of the quantum fluctuations during inflation of I cannot write. So what happens is that you develop, when each k mode exits the horizon, you develop like a flat power spectrum, like for the scalar, okay? So what you can write is that the energy density over logarithmic k is the k mode of the longitudinal mode, okay, in Fourier space. At horizon exit, this is roughly the usual thing as it would be for a scalar. Square, sorry. Okay, so the energy density in each mode is of order h Hubble to the fourth, flat spectrum, okay, at horizon exit in inflation. Now, the interesting thing, which again goes back to that fact, the fact that the mass squared of the vector has a g mu nu factor in front of it, so there is a 1 over a squared. Now you have to follow the evolution of this mode super horizon. So they exit the horizon during inflation, and then they re-enter in the radiation-dominated era. If you follow all these modes, as they did very carefully in this paper, then you can show that after they re-enter the horizon, the power spectrum of this guy is actually very peaked at some scale, which is k star. And what is k star? First, let me draw a picture, actually. So let me go there. So what happens? And what is beautiful about this is it's built in, okay? So if there is a vector which is massive during inflation, this happens inevitably, okay? So this is unavoidable. And at the end of this evolution, you get a power spectrum. Let me call it P delta, so 10 to the minus 9, 1, okay? And here I have K, the mode. Let me put K star here. And so first let me give you this estimate. So if you fix the mass of the vector to 10 to the minus 5 eV, Hubble during inflation at 10 to the 14 GeV, okay? What you find, again, this you can find by explicit calculation because you can follow all these modes. So given the parameters of your game, you have a unique determination of K star. So this K star would be with these parameters, okay? 1400 inverse parsecs. And what happens is that around that scale, you do get a power spectrum that looks like this. So the slope here is it goes like k cubed, and on this other side, it goes as k to the minus 1, okay, at these scales, around these scales. And down here, no, this is the Kobe value, like some few times 10 to the minus 9. So this kind of dark matter, dark photon dark matter, so it inherits as it should, the adiabatic fluctuations at large scales, okay? So here we are at scales of inverse megaparsecs and whatnot, okay, on this side. So cold dark matter, proper dark matter, So these are the adiabatic fluctuations. And this peak here, which is a high peak, okay? So here the power spectrum can be almost of order 1, close to 1. So, but this is at a scale, no, which is of order parsecs, okay? So it's completely fine. It's not excluded by any power spectrum measurements. And this peak is due to the fluctuations I was talking above. From really the production mechanism, okay, during inflation. So beautiful picture, okay? So this seems much cleaner, no much trouble, not compared to the misalignment craziness that was going on. So very interesting. Now, very good. Let me write that. So there are two things. Indeed, this I should write. Let me write it here. Yeah, this. Let me erase this. So when you go through the whole calculation, first you have that the abundance, let me call L for longitudinal mode. Oops. So this is equal to 10 to, 6. I decide to write in GeV rather than EV, whatever. And then Hubble during inflation over 10 to the 14 GeV squared. So you have this. And when you go through the whole calculation of how these modes evolve, what you get is that the K star, the parameter you're interested in, to the minus 1, is roughly equal to 10 to the 10 kilometers. And exploiting, so if you ask that this guy is 100% of the dark matter, you get a relation between the mass and Hubble. And when you plug everything in, you find this times 10 to the minus 5 EV over MA square root. So that's how it scales, okay? And again, this assumes that it's 100% of the dark matter. Good. So I guess this answers your question, right, Marco? Okay, good. Now, what? Right, exactly. So, right, good. So the point is, so this is, you cannot go below this mass because otherwise the Hubble during inflation is excluded already. So you can only go higher, which means that the scales of these clumps can only be, at most, can be something like that. Otherwise, smaller, yes. Good. Now, so far, I've told you about a bunch of works of other people. Let me mention in 2 minutes something I did with my collaborators. Good, let me go back here. So, when should I stop, by the way, Diego or Marco? Okay, good. So, no, we'll stop before that. Okay, good. So, I'm a terrible person because I'm quoting, you see all the names selectively, which I didn't do for Nakayama at all, so sorry about that. So this is work I did with these people. Oops. There is also a funny sociological story, but I'm not gonna waste your time with that. Ask me later if you're interested about this. It's just that there were 4 papers that came out the same day, but that's it was kind of interesting. But okay, so And the other funny thing to me for the story is that all these people, so Mar Bastero, Jose Santiago, and Roberto Vega Morales, they're all in Granada. So a combination of Spanish, Latin American, and Italian. So to me, it's amazing that we made the deadline with the other groups, but that's also another story. We were very proud of that. Okay, so what did we do? We considered something slightly different. Oops, so I keep rewriting this. Good, so I want to write it like this. Alpha over 4f, phi. Well, we were not the only ones, okay? This was this kind of coupling, which axions experts recognize as the usual axion coupling to photons. So the tilde is important here, so it's the FF tilde, which is E dot B, right? It's not E squared plus B squared, okay? So it's the parity odd combination. So the reason why this coupling is interesting is for the following. So now let me write again the equation of motion. Now I'm writing it for the comoving field, and instead of I, I'm putting plus minus for the right and left polarizations, okay, of the vector. These are the transverse polarizations, right? There is also a longitudinal polarization because this is a massive vector. I'm not gonna bother writing that equation. That equation is actually not affected at all by this coupling. So the equation for the longitudinal mode doesn't change compared to what G, MR, Graham, Mardon, and Rajendran had. So the longitudinal mode production, as I briefly explained for their model, also applies here. It's there, it's inevitable. But there is something else here, which is for these transverse modes, you have this equation of motion. Which is okay, good. So alpha okay, so what is interesting about this equation of motion? So first, let's work in the regime where the mass is very small, okay? So indeed, actually, for the mechanism that I'm about to discuss, I can start with the massless photon. It doesn't matter. It can be, I only need the transverse modes, okay? So let's neglect the mass, which means we're putting ourselves in the regime where the mass is very, very small, say, compared to Hubble, in this case, for instance. It's customary. There is a lot of literature on this coupling for many reasons, okay? So if you're interested about other things, ask me later, or now, or never, also is fine. So it's customary to define this dimensionless quantity, which very inconveniently is labeled the same Xc as the coupling to the Ricci, but now this is a different thing. So the important point now here is the following. So introducing this and neglecting this mass, again, what do I have? I have the equation of a damped oscillator, where the driving frequency of the oscillator for different K modes is given by K squared over A squared plus minus 2H C K over A, okay, where I'm neglecting the mass. So I just translated the coupling into this parameter Xc. Now, the reason why there is a plus minus is because I'm coupling to FF tilde, so this is crucial. So coupling to the parity odd operator inevitably leads to treating the two polarizations, the two transverse polarizations differently, okay? So now it's a matter of just, of conventions in the sense that let's think of phi as the inflaton, okay? So as the inflaton is rolling, think about slow rolling for the time being, okay? So phi dot will roll in one direction, you pick, it's a convention. Whatever direction you pick, inevitably, either the plus or the minus mode leads to the fact that I get some negative frequencies, okay, for low K modes, which means for for large wavelength modes, right? Because indeed, this condition is simply that this K over A, K is the comoving momentum, so K over A is a physical momentum. So for modes that are smaller than this quantity, omega square K is negative. What does it mean? It means that this is a tachyonic instability, so the solution is not an oscillating solution, but it's an exponentially growing solution. So what physically this means is that I am packing a lot of photons with low momentum, a lot of them like one on top of the other. So a good description of this system is a classical system where I have like an electromagnetic field, really, because I'm packing a very large number of photons with long wavelength. What is a wavelength, typical wavelength of these photons? We can read it from here. Not going to go through the math, but typically this parameter, dimensionless parameter xi is of order a few, okay? 3, 5, which means that the physical momentum of these photons that are mostly tachyonically produced is of order Hubble times a few. So what this mechanism is giving me pretty much a classical electromagnetic field with a coherence wavelength of the order of the horizon, okay? So within the Hubble horizon, I have really a classical ENM field. And so, good. So what does it mean? So now it means that I have energy density in the form of a dark electromagnetic field. So now inflation ends, I reheat. We didn't study the reheating dynamics that are complicated. We're actually studying them now, but I don't have any answer about that because it's a big mess for some experts in the audience. I think know about the mess I'm referring to. But anyway, so the point is, you create this energy density. After you reheat, so by the way, as long as inflation goes, the inflaton keeps pumping energy into this mode. So what happens is the inflaton gives up some of its kinetic energy, right? Because its frequency you see is proportional to phi dot. So what really matters is the kinetic energy of the inflaton. So the steeper the slope of the potential for the inflaton, the more efficiently you produce these modes, okay? Of course, you should worry also about these modes back reacting on the dynamics of the inflaton. We always stay in the regime where the back reaction is negligible, so we can treat everything analytically. If you want to study the regime, you need to go numerically. So the point is, after inflation, this thing is an energy density which now redshifts like a massless electromagnetic field. So it redshifts, the energy density redshifts as 8 to the -4. But now remember, there is a mass. This mass was small and was negligible at production, but there is a mass. So as this thing redshifts, the wavelength, the K over A, also redshifts, okay? So the momentum goes down. Eventually, the momentum will match the mass. The time that happens, it means that the dominant modes of this guy become non-relativistic. And of course, this has to happen before matter radiation equality. And after that, this electromagnetic field is a massive electromagnetic field, and it redshifts like non-relativistic matter. So, okay, victory. I have a dark matter candidate, okay? Now, if you go through the math, what you find is this. Now T is for transverse. Just to tell you how it depends on the parameters involved here. This goes as the 3/2. And then, oops, I should also tell you what these guys are. So xi I introduced there. Xi end is the value of the parameter at the end of inflation. This form, which is analytic, is derived by doing everything analytically. This is not extremely precise. The reason why it's not extremely precise is that to derive everything analytically, you can only do so during slow roll when xi is constant. When xi is constant, I have an analytic solution to this equation for the gauge mode. Of course, actually, this is more relevant towards the end of inflation, as I said, because phi dot increases towards the end of inflation, and that's where I get the main production of these modes. But to treat that, you need to do it numerically, so there is this is interesting to see the parametric dependency, okay? But then we studied everything also numerically to get more precise numbers for the density and everything. These parameters are, I parameterized, so the energy density during inflation is given by this. And then we parameterize how much goes into radiation, visible radiation energy density with this parameter epsilon r, okay? So epsilon r is smaller than 1. So a fraction of the energy initially stored in the inflaton goes into visible radiation. And this epsilon h is just that, as I told you, this thing is more important towards the end of inflation. So at the end of inflation, your Hubble parameter will be slightly smaller. So the way we parameterized it is like this. Okay, so it's a factor of epsilon h. So epsilon h, we took it to be a number of 0.1, just to get a rough estimate. Again, we did everything numerically more precisely, but just to see how these things parametrically depends on that. Now, maybe I can go back to this plot. Psi end, in our models, the largest we took was 9, say. Sorry? Yes, yes, right. Yes, yeah, absolutely. But again, what is even more important than that, no, is that when you compute things properly, you really have to account for the fact the phi dot is changing at the end of inflation. So at that point, you can throw the epsilon h away. So you do things numerically, and you really follow the evolution of h, of phi dot, and of psi also. So psi is time dependent, and you follow all of that. So this definition is not really so relevant for psi end in that sense. Yes. So let me try to answer and then tell me if the answer makes any sense. So I would say that, so during inflation, phi dot is really very well approximated by a, and then I do have an analytic solution to that equation, okay? It's in the form of Bessel functions and whatnot. So I would say if I only include that and I neglect the production at the end of inflation, this analytic expression is completely fine. It's fine, but it's by far an underestimate of the energy density you put into dark matter because you're neglecting the production when you exit slow roll. And that part of the production is actually even more important. So I don't know if this answered your question, but it's to say during slow roll, constant psi is an excellent approximation. But it only captures a part of the production, it doesn't capture the main part. To capture the main part, I need to do things numerically. Does it answer your question? Good, yeah. Diego, you had a question? No. I mean, it seems that you have, so the photon needs to be heavier than the one. Yes. Well, there is actually, here there is a lot of room because of this exponential thing, okay? So, yeah. No, I can show you, here I'm better showing plus, but it actually goes the lowest possible mass is almost the same as Rajendran and possible. Because the point here is that I can play with the exponential here. So I told you psi n to be 9, but it can be 3, it can be, I mean, the parameter space for this kind of models is huge. It's really huge. Okay, so now what we did, not in 2018, but in 2021, you see, so finally the Spanish and the Italian nature of the group came out, so we took it very easy and slow. So we did compute also the power spectrum. So we pretty much repeated in some sense the analysis that Graham, Mardon, and Rajendran did for this model, okay, following the modes. And for our model, Actually, this is slightly different. What happens is also we do have like a similar thing, which is we do inherit the adiabatic fluctuations on large scales. We have no issue whatsoever with isocurvature perturbations, and the reason is the same as here, meaning that the power spectrum peaks at some k. Here you have to prolong this, okay? So for us, it's something like this. I don't even remember, this is not even anymore k cubed and k to the minus 1, but I don't remember what these powers are. I can check later if anybody's interested. But just to say that same for us, we do have a power spectrum that peaks at small scales, and this k end, anticipating Marco's question, which wouldn't come anyway, but let me write it anyway. So in our model, the peak would be 10 kilometers, and then if I parameterize with the same epsilon r and epsilon h that you have there, this would be okay. So in our model, we also get, let's say, clumps, small scales, but even smaller scales compared to the other one. And as I mentioned, okay, now conveniently I have both expressions here on the same board. So we do have that production in our model, but we also inevitably have this production. So one prediction of that action above there, okay, with our coupling, is that if somehow you manage to measure the power spectrum in these regions, all the way out there, you could see two peaks. Possibly, yes. Oh, this is a good question. I don't know. The straight answer is, I don't know. It's yes. Well, so right, right. So it's not exactly. It's not obvious. Also, wait. So here I didn't draw it very well. I mean, the main point I wanted to convey is that there are possibly two peaks, but this peak I think to be, yeah, p delta, yes. So this is actually, so our peak is a bit closer to 1 even. I think it's around 0.1. Again, it depends on the parameters now that you choose. And for the for these parameters, for the other, well, also in our model, because it's also there, it's of order 10 to the minus 2, the p delta at the peak. This dark matter power spectrum, yes. It's not the total density, exactly. So, I mean, I would doubt actually that you would form black holes, but I didn't really think about it. It's, I agree. I agree. So it's, yeah. That you are? Yes, 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 yes. Yeah, sorry, you say the K would move to smaller values, so larger scales, yes, 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 yes. Yes, this mechanism. So if I remember correctly, again, if you push all the parameters to the extreme that you can, I should look, you see, I mean, this was 2018, so my memory is bad. But I think the lowest mass was, again, of order kind of this mass, kind of 10 to the minus 5 EV or so. It was hard for us to push it lower than that. By the way, this is a good question, because I would say one of the push for these models and whatnot was really, still today, I would say, in some sense, is a push to go as low as you can, okay? So can you come up with a mechanism to go to 10 to the minus 20 EV? Oh, and by the way, in 2018, as I mentioned, there were 4 papers that came out. One was this paper by Jeff Drower and company, which was a slightly different mechanism. I don't have time to talk about it, but they claimed they could go to 10 to the minus 20 EV or so. It's true that to get there, they were going in a region of couplings that were ridiculously small also, but yes. Sorry, so Pratik and company, Pratik was the reason why we participated in the putting out the paper altogether. So good, so as Zach is mentioning, so out of the 4 papers that day, there was this paper by Pratik Agrawal et al. I'm going to say et al. Because there were a few authors. So what they did is also, they did consider this coupling, but for them, phi was not the inflaton, but was the axion. Maybe even the QCD axion for them, probably. No, it didn't matter. Good. But so now the point is that they studied a much, much more complicated regime. So the equation for them was exactly the equation I wrote, but the mechanism of production of the dark photon for them was in the regime where phi, the axion, was oscillating. Okay, indeed, remember, so the axion is a scalar, so as long as Hubble, the friction is high, the scalar is stuck. So phi dot is 0, there is no production. When phi starts moving, starts oscillating, and then you turn on the production. But now this production phi is oscillating. So the solution to that equation, good luck, is a mess. So indeed, they studied that on the lattice. And for them, the game they wanted to play is the following. You want to transfer order 1 of the axion energy density to dark photon energy density. And if you want to do that with this mechanism, you must have the mass of the axion comparable to the mass of the dark photon. Okay, they must really be within 0.5, I think, of one another. Otherwise, you don't transfer efficiently, but maybe 0.1. Yeah, I'm not doing justice to. And to study that properly, you have to do a lattice calculation, which they did, and yes, so that's another possibility also. To me, if I want to complain, because I keep complaining, that's also a bit perverse in some sense, because you have axion dark matter, which is already perfectly fine and working, but you want to set your model such that you want that energy density to disappear and go into dark photons. I mean, fine, can work. They showed it can work, but what's wrong with axion dark matter? So now let me, okay, I could stop here actually, or I could go for another 5 minutes lunch. The other 5 minutes would be on something about Zach is the expert in this room. Okay. Quickly, so I briefly mentioned this. So far I wrote this mass, okay? Just m squared, mu squared. And if you do, this, whatever, let me go here. We've known the Higgs mechanism for so long, that you would say, come on, I mean, if you are a theorist, do a better job, with these models. Okay, now the time is short, so let me think about, but anyway, so the proper Lagrangian to write, let me pick, okay, so I stick to my sign conventions, good. So, no, there is no half. Minus lambda over 4, say. So this is, for a few decades, what we have known well, okay, how to give a mass to U1 gauge boson. So this is a U1 theory. Phi is the abelian Higgs. This is the covariant derivative. And you see phi gets a VEV, which means that the gauge boson becomes massive, right? And so let me where do I want to go with that? I will try to be brief, okay? So, first of all, there is, let me write it like this. It's convenient to introduce this notation. Okay, so V is the VEV, H is the radial mode of the scalar field, and the sigma is the goldstone that gets eaten to become the longitudinal mode. Now, let me write it. Okay, it doesn't matter. But the point is that, so you have this mass here of the radial mode, which is proportional. I'm dropping factors of 2 because I didn't write them down, so I will get them wrong. There is a factor of 2 somewhere. It doesn't matter. What matters is that, so let me call G the gauge coupling, okay, in this model, GD, G dark. So what happens in this model is that you have the radial mode with this mass, and the gauge boson gets this mass. Now, it was pointed out already, by the way, in that paper by Pratik that we were just mentioning, that if you expand this Lagrangian in these fields explicitly, now what you see is that, yeah, exactly, sorry, or this, that's what I had in mind originally. What you see is that schematically, if you enter a regime in which this term is larger than that, what do I mean by this term? By the way, as I told you, what we do in these dark photon games is we pack a lot of dark photons with some long wavelength, no? Which become classical, which means that this A mu square gets an expectation value, okay? It can get a large expectation value because we're packing a lot of quanta in a state that is classical at the end, okay? So it means that this is an energy density, really, classical energy density, and it can be large. Large meaning it's larger than this energy density, which is the typical scale of the scalar potential. If this happens, this back reacts on the, in some sense, in the Higgs mechanism. And well, there are a couple of ways you can see this. Starting from this theory here, I mean, here you see this mass is proportional to the gauge coupling, which means if the gauge coupling is large enough, you can start constructing operators not only like mu square, but you can start constructing mu to the 4th, mu to the 6th. And when you enter this regime, you see that the whole tower is as important as the mu squared. So this fact already tells you that if you enter this regime and you did the analysis without including the higher dimension operators, what you're doing is not under control anymore because there are all sorts of these effects from these operators that you're not accounting for. Because in my original Lagrangian, I only wrote mu squared. I didn't bother putting mu to the 4th, mu to the 6th. But if I did enter that regime, I have no reason to neglect those operators. So first point. The other point that was pointed out a couple of years ago in 2022 by East and Huang is that if you enter this regime, what happens is this coherent field of dark photons actually prefers energetically to discharge into vortices and strings. Again, if you want more details, Zach is the person to ask in this room, I would say. And so what that means is that what you wanted for the dark photon to be the dark matter, you want this coherent field. But if there is a mechanism like discharging the coherent field into vortices, you no longer have a coherent field, so your dark matter solution is gone, is lost, okay? So the way to do the analysis kind of analytically is in correspondence to what people would do in condensed matter, so using magnetic fields. In most dark matter models, you have both dark electric and dark magnetic fields, but then East and Huang run also a lot of simulations for those situations, and it seems that the outcome is always the same, that you always destroy this solution. So if that is true, it means that a bunch of these also mechanisms, including Gram, Marden, and Rajendran, could be in trouble. I would like eventually to understand better like these points, because there are some parts that I haven't properly understood, I must admit. So maybe I will take advantage of Zach also this week to ask some questions. But this is just to say that, so there are, let's say, just to give you a feeling, for instance, and then I will stop. For instance, in the Gram-Mardon-Rajendra mechanism, if you insist on these bounds from avoiding vortex formations, this translates into a coupling that should be okay. Now I didn't do the derivation; is not so hard, but just to tell you that this kind of reasoning, okay, if correct, which I guess very likely it is, tells you that you're going into regions of parameter space that are unpleasant. What's the right word? But it's you have these tiny numbers that are never. Theoretical physicists are not big fans of this. And then I will stop here. And Zach and his collaborator David, right, Cincinnatis, wrote a couple of papers in the past couple of years where they pointed out also another interesting thing related to this, which is now we're talking about the dark sector here, no? But remember, good, I still have that picture there. I mean, eventually, if this is what nature decides, chose for us, for the dark matter, the handle we have to test it is the kinetic mixing, okay? So now, naively, and that's exactly what you expect, the kinetic mixing will be given by the visible gauge coupling E times this dark gauge coupling, typically over, say, 16 pi squared, because it's a loop effect. You have a real photon, a dark photon, and then you have, let's say, fermions that are charged under both visible and you want dark. So the mixing comes out one loop, and that's why you put this. But now the point is the following. Here we know what it is. No, we measure it's the electric charge. But if GD, by these considerations, is forced to be this, as Zach and David pointed out, you can look at their papers, the plots are dramatic. So taking this constraint here and the naive estimation of the mixing being this, all the region of parameter space is gone, completely gone. So then you have to come up with, as they did, with other models to come up, let's say, with the dark photon, dark matter model, which becomes testable. I hope I didn't misrepresent, Zach, what you did. Okay, good. I will stop here.